Yeah. So in the last class, so we have defined what is a heat engine and how the cycle, okay, inside the heat engine it runs. Okay, so yeah, yes. So the Kelvin Planck statement. Just let me switch off my video. Yeah. So what actually the statement of this Kelvin Planck about the second law? It is impossible for a heat engine to produce net work in a complete cycle if it exchanges heat only with bodies at single fixed temperature. Okay, means when a system which is under cyclic operation, so it will produce work. Okay, so when it will exchange, when this heat engine will exchange heat with two temperatures. Okay, so here this is one reservoir at temperature T1, and this is another reservoir, means where the heat will be given. Okay, so this is called sink. So the one is source from where heat is taken, and another is the sink where heat is thrown, okay, or discharged. So a heat engine will produce work only when it will be operating in between two temperature. Okay, so here it is said that it is
Sir,
impossible to produce net. Yes, 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 yes.
sir, your voice
Okay,
is
Rehan.
lagging, sir. Continue.
Oh, actually, there might be some network issue. Uh, Let me know, okay, if in between the network actually it is fluctuating, my voice is fluctuating, then let me know. Okay, just you respond. Now it is coming clearly, Rehan,
Yes. Yes.
Shankar. Okay, okay.
Okay, sir.
So if it
Yes,
fluctuates,
sir.
then tell me, okay, in between, no problem. If you just yeah, tell me. Okay. So the Kelvin Planck statement, so it basically states that it is impossible for a heat engine to produce net work in a complete cycle if it exchanges heat only with bodies at single fixed temperature. That means if this heat engine, okay, the component which is in between the source and the sink, this is a heat engine, as because this operates in a cycle, so that is why it is shown in this way. Okay, one arrow mark you will see here and here, means it is operating in a cyclic process. So it will produce network when it will take heat, at the same time it will reject heat. Okay, means it will give some heat to the surrounding, okay, or to the sink. If this Q2 is 0, means if it does not give some amount of heat to the sink, so it cannot produce network. That is what actually it means. Okay, means this Q1 amount of heat direct, it cannot be converted to equivalent amount of W. Okay, but reverse is possible. With an equivalent amount of W, you can produce equivalent amount of heat. Okay, so here this part it is necessary that when some heat is produced from a cyclic engine, some heat should be rejected. Okay, so here this is incomplete because see here Q2 equals to 0, means the system is producing some work, but there is no heat which is giving out by the system to the sink, though it is shown as giving heat, but the value is 0. Okay, so this type of machine is called as PMM2, okay, perpetual motion machine of second kind. So if you are asked to draw what is a perpetual motion machine of second kind, then you need to draw this one, and at the same time you need to justify your answer that if there is heat taking by a cyclic system or heat engine, and if there is no heat going out from the system, and at the same time if it is producing W net which is exactly equal to Q1, so that kind of system is called as PMM2 system. Understood? In Kelvin Planck statement, so basically you need to draw this to drawing. Okay, So this is Kelvin Planck's statement about second law of thermodynamics. Now let's come to Clausius statement. Okay. So what is Clausius statement? So Clausius statement of second law gives that it is impossible to construct a device which operating in a cycle will produce no effect other than transfer of heat from a cooler to a hotter body. Okay, that means what? See, generally by nature, so as I have told you that the second law will give you the direction of the energy flow. Okay, so generally we know that heat naturally flows from lower body, isn't it? Water always falls from higher elevation to lower elevation. Okay, we always grow old, okay, not younger. So these are natural laws. Okay, so here, so heat cannot, just wait. Okay, I have a call. uh, yeah, so the Clausius statement is that if you actually wants to transfer heat from a cooler body to a hotter body, so you need to do some external work. Okay, means you need to work upon the system. So this example can be easily understood by taking the example of your motor pump which is in your home, okay, house. So how it is possible? See, from second floor to the ground floor, water can easily comes through the pipe. Okay, if you just open the valve, so it will comes down easily, isn't it? So a flow will happen inside the pipe, okay, through the pipe, and you can have the water at the ground floor, isn't it, by opening the tap. But if you want to just discharge the water to the second floor tank, okay, from the ground floor, so what you need to do? So you need to pump it on, isn't it? You should have use one pump, okay? So that pump will be run by motor, okay, means electrical energy. So basically, so this is the statement of Clausius statement. Okay, means to flow heat from a cooler body to a hotter body, so you have to do some work. Okay, that is W. So here it is said that, but statement is different. Okay, so when you are asked the statement, so you need to write like this way. Okay, in direct speech, that it is impossible to construct a device which operating in a cycle. Okay, in cyclic operation, cyclic, just like the heat engine. So cyclic operation should be there. Okay, means initial state and the final state should be same. So it should be working in a cycle, will produce no effect other than transfer of heat from a cooler body to a hotter body. Means from transfer of heat from cooler body to hotter body, if only the device is producing heat, it is impossible. At the same time, it should produce some work also, or some work should be given to the system. That means that from cooler body to hotter body, if you want to transfer heat, you should give some work. Okay, means extra work it is necessary, because to pump water from ground floor to the second floor, so we need one water pump or electric motor, okay, to run the pump, isn't it? So that means these examples, actually you can take the same analogy to understand this the statement. Understood? But you cannot write that concept of water flow, because that is fluid dynamics concept. Okay, and here we are dealing with heat and work. Okay, energy transfer. Understood? Only to understand, I have taken the example. So now how this can be actually understood, okay, and what are the devices which works upon this principle, okay, second law of thermodynamics. So yesterday we have day before yesterday we have this one considered, we have taken these heat engines, okay, how these works. It is written, okay, here, but I have already mentioned all the points. Just if you just go through it, okay, so just give a reading, then you will easily understand what is a heat engine. Okay, yeah, so we took this example, okay, and the elaboration it is given here. Okay, everything I have taken, okay, in the last class, all these things, just you go through this stanzas. Okay, the turbine will produce some work, and at the same time you need to pump the and here you pump the fluid. Okay, again it will go here, and again it will complete a cycle. Okay, so cyclic process will happen, and finally you will be able to find out the thermal efficiency eta. Okay, so eta is 1 minus q2 upon q1. So why there is q1 minus q2? Because we are actually concerned about this w net, because we need work, okay, at the output for both these cases, okay, for both these heat engines. So in heat engines, just like our motor engine, just like the generator, okay, just like the thermal power plant, so what we need? So we need the power at the exit, isn't it, to run the wheel or to get the electricity. So we need the work, okay, here in this system. So we need the work at the turbine shaft to run the generator, isn't it? So this is our output. Here also, let's say this is piston cylinder arrangement. So we need to run our vehicle axle, okay, or the wheels. So our output will be in the form of work, okay. So this is the desired output. So WT, here it is written W net. You can write W net, okay. So W net by Q1, because Q1 was the energy which was taken from the surrounding, okay, or from taken some source, okay. So this W net, so W net will be, there are two work transfer, WT minus WP, because the work it is given to the system, so it will be negative. So work is done by the system, by the turbine, so it is positive. So WT minus WP will be equals divided by Q1 will be the thermal efficiency, okay, for this heat engine. Understood? Yeah. Now let's come to this Clausius statement, okay. So where you will get this kind of actually application of this Clausius statement, because Clausius statement says that if you want to transfer heat from a cooler body to a hotter body, you need to do extra work, okay. So just mind those lines, okay, what it is written actually, from cooler body to hotter body. So where it happens? So generally in refrigerator, okay. So refrigerator, inside the refrigerator it is cold, okay. Outside the refrigerator it is atmospheric air, okay, so which is hotter, and you need to maintain your refrigerator at a lower temperature than the atmosphere, isn't it? But how it happens, okay. So to understand the concept of refrigerator, so this is the basic drawing, okay. So this is the basic diagram, and here this body A is the refrigerator, okay. So this is the freezer, and here this is your room, okay, atmosphere. Here this is your room, where in, let's say it is kitchen, okay. So where your freezer it is placed, okay. So our motive is to place cool this freezer, okay, because the temperature inside the refrigerator it is low, very low, okay. It may be around 6 degree, 7 degree, or 2 degree, okay, 1 degree, and your atmospheric pressure, room temperature, it may be 30 degree, 35 degree, or nowadays it may be around 20 to 22 degree, okay. So our concern is upon this system. This is body A, means this is the refrigerator. So what will happen? This refrigerator is placed where? Just amidst the atmosphere, isn't it? So though these two, body A means refrigerator or this freezer or this atmosphere, though it is showing separately, but this refrigerator, okay, refrigerator is placed amidst the, isn't it, means inside the room, and inside this refrigerator all these components will be there, though they are showing separately, they are being shown separately, but inside this body A, all these components will be there, okay. So what are those components? One is evaporator, okay, another is compressor. So compressor, I think you have, all of you have heard about this name compressor, because our tires are inflated by these compressors, isn't it? So this is one different type of compressor, but working principle is same, okay. Means something or the gas, it is compressed here, okay. So here inside the compressor, so to run a compressor, so we need a motor, okay, just like the pump. So compressor, then condenser. So condenser, what are condensers? So condensers are the devices which converts the vapors to liquids, okay. So these are control condensers. Then expander. Okay, so it may be a small turbine expander, so it will expand. So how this expansion is shown? So here it is smaller in length, okay, this area, and here it is bigger area. So expansion is happening, so this is called as expander. Okay, so these are the equipments which will be there inside a refrigerator, means this inside this body A. So what you need to do, you need to maintain this body. It is insulated, but heat will go to the refrigerator. Okay, heat will go to the freezer because of the temperature difference, because here it will be at a lower temperature and here it will be a higher temperature. So what will happen? So from higher gradient, the heat will flow, okay, to the lower gradient. Understood? So Q2 amount of heat will flow to the system, okay, or the system will take Q2 amount of heat. Understood? So due to this Q2, the temperature of the body will be T2. Okay, so this Q2 amount of heat, so what will happen? So it will be evaporated. Okay, so this will be evaporated at a temperature lower than the atmospheric temperature. Okay, so here outer temperature was how much? T1, but here in the evaporator it will evaporate. Okay, so but the temperature will be lower than the temperature of the atmosphere. Understood? So here in the evaporator some refrigerants are there. Okay, refrigerants are there. So there may be, these may be various types of ammonia refrigerator. Okay, like other type of refrigerators are, may also be there. So it depends on the manufacturer. Okay, what type of refrigerator refrigerants they are using. Okay, so the evaporator, inside the evaporator, this Q2 amount of heat, it is absorbed. Understood? Q2 amount of heat is absorbed, and the temperature, now the temperature of this evaporator is lower than the atmospheric temperature. Now this evaporator, okay, after this evaporation, so the fluid will go to the compressor. Okay, so the fluid will go to the compressor. So the vapor, because here the vapors are contained, isn't it? So the vapor is first compressed in the compressor C1. So here inside this C1 compressor, the vapor will be compressed. Okay, and in the condenser, so in the condenser what happens? So it will reject the latent heat of condensation Q1. Okay, means here inside the compressor, as because this liquid is compressed, okay, as because this refrigerant it is compressed, uh, this is not liquid. Okay, so here it will be absorbed by the liquid refrigerant and it will be converted to gas. Okay, now if it is compressed, so what will happen? So temperature will increase, pressure will increase, isn't it? So the temperature will be higher than that of this atmospheric temperature. Understood? Now what will happen? From this compressor, here also the phase is in vapor phase, but it is compressed. Okay, temperature is increased. So now when it will move to this condenser, so the vapor will be condensed. Okay, and it will release latent heat of condensation. So now the vapor will be converted to the liquid refrigerant. Understood? And it will release Q1 amount of heat to the atmosphere. Okay, and as because this atmosphere is a heat reservoir, so the temperature will not change, because I told you that from a reservoir, if you just take out, okay, 5 baltis of water, so the total volume of water will not change. Okay, so just like that, if you add some amount of heat Q1, the temperature Q1 won't change. Okay, it will remain the same because it is a reservoir. Okay, so our atmosphere is a reservoir, okay, of energy. Understood? So again what will happen? So from this one condenser, which is yeah, so where the state is the temperature is a little bit higher than the atmospheric temperature, so the fluid will go again to the expander. Okay, so the expander will what happen? So here volume will expand. Okay, so what will happen? So the temperature will be lowered. Understood? So again the the substance will be converted to liquid form, and it will flow again through this evaporator, and again it will take some heat. Okay, means from here, so your fluid was flowing, okay, refrigerant was flowing, and again they will be converted to the initial conditions. Okay, that means what? It is completing one cycle. Okay, cycle through evaporator, compressor, condenser, and expander. Okay, so in this cyclic what it is called as refrigerator, okay, in this refrigerator which is operating in a cycle, because we have seen that how it works as a cycle. Okay, because the temperature it is now same. Okay, though here it is increased and here also it is increased, but finally after the expander or turbine, after discharge of that refrigerant, okay, or the material, you will get the same temperature fluid. Okay, so here again this Q2 amount of heat will be absorbed, and again it will run the cycle. Okay, so in this cyclic refrigerator, so what is happening? The body A is maintained at a temperature of T2. Okay, so and this body is Q2 amount of heat continuously from the surrounding, and it is discharging Q2 amount of heat to the evaporator. That is why the body temperature will be constant. Okay, otherwise if we will not discharge, okay, heat to the evaporator, the body temperature will increase, isn't it? If it is constantly heated, it will be increased, but you need to maintain the temperature at a constant temperature. Okay, so amount of heat leaking to the system, amount of heat discharging from the system to the evaporator will be same, means rate of heat, not amount of heat. Rate of heat which is entering to the body A from the surrounding is equals to the rate of heat which is going to the evaporator from the body will be equal. Okay, that is why you will be able to maintain this body at a constant temperature. Okay, and here at the same time some heat should be rejected to the atmosphere, otherwise these works, okay, work transfer will not happen. Okay, this will violate the law. Okay, so at the same time the heat is rejected. Okay, otherwise this cycle will not be completed, because this will be also heated, this condenser will be also heated. If it does not release heat to the atmosphere, then again through the turbine, so you will not get that effect, and finally you cannot complete a cycle. Understood? So here basically this refrigeration effect, it is shown by this drawing. So body A, that is a temperature T2 which is lower than temperature T1, atmospheric temperature T1, because in refrigerator our refrigerator is, it should be always lower than the temperature surrounding. Understood? So here from E2 to E1, okay, means this evaporator, okay, to evaporator 1, and compressed, yeah, expander to evaporator. This is the cycle, expander to evaporator 4. Okay, then from E1 to C1, okay, so 4 to 1, this is E1. Then from C1 to C2, this is shown by 2. Okay, stage 2. Then C2 to E2, C2 to E2, it is shown by stage 3. Okay, so by looking at this drawing, so you can say that this complies to a circle. Okay, this implies to a circle. And what is happening inside in between this E1, E2 and E1, now you will be able to tell. Okay, and E1 to C1, so you will be able to tell what is happening. Okay, so inside the components of the refrigerator. Heat pump. Okay, so heat pump. So what is the difference between a refrigerator and heat pump? So here our actually concern is that we should make a body hotter. Okay, we should make a body hotter. Our here in refrigerator, our concern is to we should make a body cooler. Understood? And what is a heat engine? A heat engine is a device to produce work, okay, when it operates in between two temperatures. Understood? And here, what is refrigerator? So a refrigerator is a cyclic heat pump, you can say, cyclic engine or cyclic heat engine, where not heat engine, it is a cyclic device where a body should be maintained at a temperature lower than the atmospheric temperature. Okay, and what is a heat pump? That we need to maintain one body at a higher temperature than the atmosphere. Okay, so here in heat pump our concern is upon this system. Okay, not on atmosphere. Earlier, our concern was on the system where temperature was lower than surrounding. Now here higher than surrounding. Okay, so how it can be maintained? So see, a heat pump is a device which operating in a cyclic maintains a body, say B. So this is B at a temperature higher than the temperature of the surrounding, as I have told you. So by virtue of which temperature difference, there will be heat leakage Q1 from the body to the surrounding. Okay, so a heat pump is, this is a cyclic device. Okay, cycle, in a cycle it will operate and it will extract heat Q2. Okay, it will extract heat Q2. So to extract heat from a lower temperature to a higher temperature, so you need to do some work, isn't it? Because I have told you to, from ground floor to first floor, if you want to discharge the water, okay, so you have to just use some motor, isn't it, or pump. So just like that, you are doing some work, okay, on the compressor, okay, or on the expander. Okay, so all these components will be there. So just like this refrigerator, all these components will be there for this heat pump. Okay, so here directly from this diagram, so you can say that these will also be equivalent. Okay, so to pump heat from a lower temperature to higher temperature, work is done and the heat is pumped. Okay, now you need to maintain the temperature T1 inside this body. Okay, because Q1 amount of heat is flowing in every cycle, that is why Q1 amount of heat needs to be rejected in every cycle. Okay, then only this Q1 will be maintained. Understood? So T2 is less than T1, means T1, this body, you need to make it hotter. Okay, and it should be at a constant temperature. It is only possible when Q1 amount of heat it is taking and Q1 amount of heat it is rejecting to the surrounding. Understood? So the same thing it is written. Okay, so all these components will be there just like the refrigerator. So here one important terminology actually come into picture, that is COP, coefficient of performance. Okay, as because here this case is exactly opposite to the heat engine. Okay, here for this refrigerator or this heat pump, so our concern is to move heat, okay, from a lower temperature body to a higher temperature body. That is why for this refrigerator and heat pump, this efficiency is written by COP, coefficient of performance. Okay, and it is defined by desired effect by work input. Okay, because we need to pump from lower temperature to higher temperature, that is why input will be what? Work. Okay, and desired effect will be, for refrigerator, desired effect is what? Q2, because we need this Q2 amount of heat which should be transferred to the system, because Q2 amount of heat is coming from the surrounding, isn't it? So that is our concern is on Q2. It means if we can control this Q2, then we will control this whole system. Okay, so by putting some work, okay, because W you need to do in heat pump or in refrigerator. So Q2 by W, but for this heat pump, the COP will be Q1 by W, because our concern is what? For this heat pump, our concern is to make this body hotter. Okay, means Q1 amount of heat should be rejected to the surrounding as it is receiving Q1 amount of heat. Okay, so if you can somehow discharge this Q1 amount of heat from this body to the surrounding and it can receive Q1 amount of heat from this system, so then you will be able to maintain a constant temperature. That means by giving the input as work, okay, net work, and if you are receiving this amount of output, that is Q1 by W, net will be the coefficient of performance for this heat pump. Okay, so definition is same, okay, but desired outputs are in different regions. So for this refrigerator, this is the desired region, okay, means we need to cool this refrigerator, and for this heat pump, so desired region is, or output should be here. Okay, so we need to make this body hotter. So Q1 will be Q1 divided by W. Okay, so will be the coefficient of performance. So one relation. So what is Q1? Q1, W is what? Q1 minus Q2. Okay, because in a cyclic process, the net change of the summation of the net change in work will be equal to the net change in the heat. Okay, so Q1 minus Q2. So if you just compare these two, okay, so here Q2 divided by Q1 minus Q2. So what you will get, that COP of a heat pump, okay, considered, it is for refrigerator and heat pump, so we will be writing as COP. Okay, so COP of heat pump will be equals to COP of refrigerator plus 1. Okay, so from this and from this, if you just mathematically calculate, so you will get that COP of heat pump will be equals to COP of refrigerator plus 1. Okay, and the value can be, see, exceeds 100% without violating any law. So the value of COP, okay, or a heat pump or a refrigerator, it may be greater than 100%, but it cannot be infinity. Understood? So you need to remember that one. Okay, it should be less than infinity. Okay, means it should have some definite value. So I think all of you have understood this concept of heat pump. Okay, and in the last class we have covered heat engine. Okay, so for heat engine always there will be efficiencies, just like your motor vehicle. So if anybody asks what is the efficiency, that means the thermal efficiency they are asking. Okay, some other types of efficiencies are there, but mechanical efficiencies and all those things are there. But generally when we'll be saying it as heat engine, so we will be only saying that the thermal efficiency of the heat engine, and it is always less than 1. Okay, and for this refrigerator and heat pump, so the efficiency is basically denoted by COP, coefficient of performance, and COP for refrigerator is Q2 divided by W, Q1 minus Q2, and COP of heat pump, COP of heat pump, it will be Q1 divided by Q1 minus Q2. Okay, so I think now this concept is very much clear to you. Okay, so now let's move to a important topic, that is equivalence of Kelvin and Planck actually statement. Basically it is seen that means when you will first time when you will take these two definition. Okay, so let's take these two definition. So what you will get that it may be different. Okay, Kelvin Planck statement, it looks like that Kelvin Planck statement is not similar to what it is said in Clausius. Okay, but if you violate one statement, then the other statement is also violated. So that is what you can actually summarize, that both the statements are equivalent. Okay, so basically it is called equivalence of Kelvin Planck and Clausius statement. So okay, today now we will see what is the equivalence. Okay, how this equivalence it can be shown in between these two relations. Okay, because the statements are different. Here it is said that when some system is producing work, so it should be sharing heat with two reservoirs. Okay, so here from with source and with sink it is sharing. Okay, and it is impossible if it produce net effect by sharing with a single source. Okay, so always there should be Q2. Okay, so I will violate first. I will try to violate this law of this one Clausius law. Okay, first I will violate the Clausius law. So how I will violate? Yeah. See, the equivalence of the two statements will be proved if it can be shown that the violation of one statement implies the violation of the second, and vice versa. So let's violate one statement. So we will violate first Clausius. So what Clausius generally says, he says that it is impossible to actually see general. What is general statement? That is that you cannot, okay, a heat cannot flow from a lower temperature body to a higher temperature body. Okay, so if you want to flow heat from a lower temperature to higher temperature, you need to give some work. Okay, so let us violate Clausius law. Means there is a cold reservoir. Okay, temperature is T2, which is less than T1. Okay, this is cooler, this is hotter. Understood? Now what we will do? So we will move the means we will run this heat pump. Okay, there is a cyclic device which is a heat pump, but we will not give any work, okay, to this heat pump. Only the cyclic process will happen. We will not give any heat work from the outer source. And what we will be doing, we will move the heat, okay, from the cold reservoir to the hot reservoir, but naturally it cannot happen, isn't it? From a cooler body to hotter body, heat cannot flow. Okay, but it is assumed that heat is flowing. Okay, now now let us assume a cyclic heat engine. Okay, now let us assume a cyclic heat engine. It was heat pump where we did not introduce any work. Okay, now let us assume a heat engine. Okay, E operating between the same thermal energy reservoirs. In between these two reservoirs, this is operating. Okay, and it is producing W net. Okay, means it is produces some work. Okay, and this value of work will be what? Q1 minus Q2, isn't it? Because the difference of these two energies will give you the net work, isn't it? Q1 minus Q2. Now it is releasing heat to this cold reservoir. Understood. So what you can do, see here Q1 amount of heat it is extracting, okay, from this cold reservoir, and it is supplying Q1 amount of heat to this hot reservoir, which is naturally not possible. Means we are violating this Clausius law. Okay, we are actually analyzing on the basis of Clausius law. Okay, so here W equals to 0. So what is happening? That same heat it is input for this heat engine, and it is producing some work. Okay, when it will be sharing the other component or other amount of heat to a different source. Okay, so it can produce network. So what you can see that this is Q1, this is also Q1. Okay, so now you can remove this hot reservoir, isn't it? So directly you can feed this Q1 to this heat engine. Means upper portion just you remove it. Okay, you just imagine that upper portion is not there, because here the output is Q1 and here you are giving same amount of heat, so no need to just take this reservoir. Okay, so you can directly join this line here, isn't it? So what is happening? So this heat engine is producing network when it is sharing heat only with a single reservoir, but it is impossible by Kelvin-Planck's law, isn't it? So it violates the Kelvin-Planck's law also. So when you violate the Clausius law, that is when there is no work, you are just flowing heat from a cooler body to a hotter body, then what you have seen that in the heat engine, that same amount of heat if you just insert, then it will produce W net. Okay, so which is not possible, because this heat engine is produce net work when it is just taking heat from this reservoir and it is giving heat to this reservoir. So here this is impossible. Okay, so which violates the Kelvin-Planck's law. Okay, so violation of one law results to the violation of the other law. Understood? So that is why you can say that this Kelvin-Planck's law is equivalent to Clausius law. Okay, so similarly you can do the other thing, reverse thing, that is if you just violate this Kelvin-Planck's law, okay, or statement, then finally what you will see that Clausius statement or Clausius law is also violated. Okay, or it also violates Clausius law. Okay, so that is one homework to you. I have given the notes, just you read it out and you try to understand. Okay, the second condition, that first you violate the Kelvin-Planck's law, then what you will get that Clausius law is also violates. Okay, so this is one homework to you, the second part. Okay, so you need to do by yourself. Okay, and if you have any doubt, then you can ask me in the next class, and from today's class also, if you have any doubt, then you can ask me now. If you don't have the doubts, then you can leave the meeting. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes.
Thank you, sir.